Welcome back. We're going to switch. We've been talking about buffers quite a lot, and we're going to get to buffers. Don't worry, there's buffers ahead of us. But we're going to start on titration now. And if we were in person, one of the questions I would ask is, who likes titration? And usually everybody goes, but there's usually like two people that go, oh yeah, that was so much fun. Those people love precision. Titration is all about precision. So in Chem 50, in your first semester general chemistry class, you probably talked about titration, and you talked about the equivalence point of a titration, and you drew some curves, and you used phenolphthalein to make that nice barely pink solution, and you might have cheated and blown on it to make it clear again, or whatever you did. Now, what we're going to do in this class is we are going to talk about titration in excruciating detail, which means we're going to calculate every single point on that titration curve. We're going to be able to calculate the pH at any point on a titration curve of a strong acid with a strong base, which is what you did in Chem 50, but we're also going to go for weak acids or weak bases titrated with strong acids and strong bases. So, fun, fun, fun. What we're going to do is we're going to fill out this chart as we go, which is the pH versus volume of base added. We're going to use as our example 0.100 molar nitric acid and HNO3, and we're going to start off with 50.0 milliliters of that, and we're going to titrate with 0.100 molar sodium hydroxide. Right? And if you remember what that looks like, it means down in here you've got your nitric acid, and we know it's a strong acid, so we don't really have HNO3. What do we have? We have H plus and NO3 minus because it falls apart in solution. And then in our burette, we've got our sodium hydroxide. And we're going to be dripping that in here as we do our titration. So, like I said, we're going to calculate every point on that titration curve. The easiest one to calculate is our starting. Right? We've got 0.100 molar of a strong acid HNO3, and we've learned that we can just take the negative log of that and find that our pH is going to be 1.000. So we can go to our curve over here and say when we've added no base, our pH is a fantastic 1.00. So now we're going to start adding some base. We're going to add 10 milliliters of base. So add 10 milliliters of base, and we're going to try to see what happens to our pH. So we know that, right, our base, sodium hydroxide, our H plus and our OH minus are going to react to make water, and it's going to neutralize that. But how are we going to do all of this? And it turns out, because we've got these volumes changing now, right? We have 50 milliliters. We're going to add 10 milliliters. So now we have a solution of 60 milliliters. We can do a dilution problem where we figure out our initial concentrations. We figure out our final volumes. We do our M1V1 equals M2V2. Then we do our reaction and things like that. But it turns out that's a whole lot of work. So one of the tricks we're going to use in this class is when volume is changing, work in moles. When volume is changing, work in moles. Why? Because if I've got 1 mole of something and then I dilute it to double the volume, what do I still have? I still have 1 mole of that something. That's the cool thing. If I put in 5 grams of sugar and then I add 100 billion gallons of water, I still have 5 grams of sugar, right? Which is the same number of moles, or which is a certain number of moles of sugar. So when volume is changing, working in moles makes our life a whole lot easier. Now, we will have to convert back to molarity, because when we're calculating pHs, if we're using Ka equations, things like that, that's all got to be in molarity. But we're going to do most of our work in moles and then only use molarity at the end when we have to, as opposed to trying to figure out dilutions at every single step. That's much, much more tedious. So what we're going to do is we're going to say, hey, what's our starting moles of acid? And in that case, it was 50 milliliters times 0.100 molar. And the astute among you will be like, Professor Clements, no, 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 no. Molarity is in moles per liter, so I've got to convert that into liters. And you can do that if you really want to. No problem, that's what you should do, then you'll get pure moles. But it turns out, remember this milli, right, is just a 10 to the minus third. And so if I multiply 50 times 0.1, I get 5.00 millimoles. Yeah. Do the math. If you actually convert that to liters, you get 5.00 times 10 to the minus third moles. But what's 10 to the minus third? It's milli. And so we'd get 5.00 millimoles. And so we're going to use this trick a lot too. Instead of converting to liters, since most of the stuff we measure in the lab is in milliliters, we're actually just going to work in millimoles. You're like, oh, that seems like a lot of extra work to do millimoles. No, it's great. It means we never have to convert our milliliters ever again. When we want to convert millimoles back to molarity, we actually can just divide by milliliters because the millis cancel. Very cool. You'll see me do that in just a sec. So we had 5 millimoles of our acid. Since we added 10 milliliters of base, and it was 0.100 molar, that is going to be 1.00 millimoles of OH minus. Now, we've got to figure out what's going to happen here. Mostly for the strong acid, strong base, most of us can figure that out in our head, but let's go ahead and write it out. Right, this is going to be 5.00. This is going to be 1.00 millimoles. And certainly this is going to be our BRI, right? What are we going to run out of first? We're going to run out of OH first. 1.00 minus 1.00. So we're going to have 4.00 this, 0 of this, and we don't really care about water. It doesn't really change its concentration, so we don't care about how many moles of water we made. So we've now got 4.00 millimoles of acid still. How are we going to find that pH? Well, we need concentration to find pH. It's tempting to just plug the 4.00 into our pH equation. That's not going to give us a very good answer. But like I said, one of the cool things about using millimoles is we can now go back to molarity by dividing by milliliters instead of dividing by liters. So again, less conversions. So do we divide by our 50 milliliters? And the answer is no, because we also added our 10 milliliters. In fact, both of those had more sig figs. So let me do that. 50.0 milliliters plus 10.0 milliliters. And it looks something like that. So 4 divided by 60 gives me a concentration of... couldn't find in my notes. 4 divided by 60 gives me a concentration of 0.0666 molar, and a log of that is going to be 1.18 as my pH. Okay, so that's my H plus concentration. And it's going to be that divided by my 60 milliliters. It gives me a pH of 1.18. So when I added 10 milliliters of base, I got myself a pH of 1.2. So 10 milliliters of base is right here. I got myself a pH of 1.2. Not a very big change in pH, is it? Now, I could go and do this again for 20 milliliters of base, for 30 milliliters of base, for 40 milliliters of base. So I'm going to go ahead and just give you those numbers as opposed to going through all those tedious calculations again, but it would be exactly the same. Right here, I just put in a 20 milliliters of base, and I figure out that I have 2 millimoles of hydroxide. Down here, I'd have 3 millimoles. Here, I'd have a total of 20 milliliters, and that's all that would change. Okay. So when I add 20 milliliters of base, my pH is 1.37. 30 milliliters, my pH is 1.60. 40 milliliters of base, my pH is 1.95. So I can go ahead and plot those. 1.37, 1.60, and 1.95. Right? Not a very exciting curve right there so far. It's pretty flat. It is rising over time because we're adding base, right? It's not like we're adding nothing. We're adding base. We're using up our H+, but we still have a lot of excess H+. And anytime you've got a bunch of excess H+ around, your pH is going to be relatively low. Okay. So why did I stop at 40 milliliters? Because something magical happens at 50 milliliters. What magical thing happens at 50 milliliters? 50.0 milliliters of base added. Remember, it was 0.100 molar. 50.0 milliliters times 0.100 molar is 5.00 millimoles of base. If I made my H+ and OH minus goes to water table here. That's going to be 5.00, 5.00. I'm going to use up all of it. I'm going to use up all of it. And I'm going to have nothing left. If I have no excess H plus and I have no excess OH minus, what do I have? I have just water. What's the pH of water? My pH of water is 7. Don't try to take the log of 0. That won't work so well. You just have to remember that water has a pH of 7 from its autoionization. So when we get up to this, wow, that is quite a jump. That is quite a jump. And we could calculate the pH at any point from 40 to 50. We're just not going to do it, but you'd actually get right answers. You go from 40 to 50, you're going to get the right answer every time. All right, so at 50 milliliters, we had a pH of 7. What about at 60 milliliters of base times 0.100 molar is going to be 6.0 millimoles of base. We're going to write this out again. 5.0 millimoles, 6.00 millimoles. And this way, we're going to be limited by our acid. So we're going to have minus 5.00 millimoles, minus 5.0 millimoles to give us a total of 0 and 1.0 millimole of excess base. By saying excess base, that just means at the end of everything, we've got more base left over, so we call it excess base. We're going to find the concentration of OH minus is going to be 1.00 millimoles divided by 50 milliliters to start, plus 60 milliliters added. That's going to give me 1 divided by 110. And it's going to be a concentration of 0.00909, the good old 909. Molar, so my POH is going to be the log of that. And you're like, oh yeah, that's going to be POH, not pH, because it's the OH minus concentration. Yeah, 2.04, which means my pH is going to be 14 minus that, or 11.96. So my pH is 11.96 at 60 milliliters. 11.96 at 60 milliliters. We're way up here. Boom. And if you remember, those pH, those titration curves were very, very, very sharp. And we're seeing from the calculations that that's obviously going to be true. We're going to get very, very sharp pH calculations. Okay, I'm just going to tell you, at 70 milliliters, you get a pH of about 12.22. And that's about all I have in here. But you can see kind of that general shape of the titration curve coming in as sharp, and then you get the plateaus both at the beginning and the end. And that's going to be a strong acid plus strong base. So when we have a strong acid and a strong base, we get this very sharp titration curve. The pH at the equivalence point was 7. Now, what do we mean by equivalence point? It turns out that equivalence point has a very specific definition that most people aren't aware of. They tend to think it's when the concentration of H plus and the concentration of OH minus are equal. But that's actually not the best definition. The equivalence point is when the moles of H plus is equal to the moles of OH minus. You want to do that in moles, and specifically moles of H plus equals moles of OH minus. That is going to be the definition of equivalence point that we use over and over again in this class. So that is our curve here for a strong acid and a strong base. So your turn to try to figure out a point on that curve, or a point on a similar curve. What is the pH of 50 milliliters of 0.2 molar nitric acid titrated with 95 milliliters of 0.1 molar sodium hydroxide? I couldn't even see my face on that one. I have no idea what I was doing. All right. What did you come up with? Hopefully, you're going to find out some millimoles, figure out what you have excess of, and then go from there. I've got 50.0 milliliters of 0.200 molar. That's going to be 5 times 2 is 1. Sorry, 5 times 2 is going to be 10.0 millimoles of H plus. For my acid, that's my acid, my base is going to be 95.0 milliliters times 0.100 molar. It's going to be 9.5 millimoles of OH minus. We have excess H plus, right? We're not going to write the H plus OH thing here. We have excess H plus. We have more H plus than OH minus by 10.0 millimoles minus 9.5 millimoles. And so we have 0.5 millimoles. And this should actually happen to 0.50 millimoles of H plus. If we want to find that concentration, let me write that a little clearer. The concentration of that, we're going to divide by the total volume, which is going to be 50.0 milliliters plus 95.0 milliliters. That is going to give us a concentration of 0.5 divided by 50 plus 95 is 3.4 times 10 to the minus third molar, and it's going to give me a pH of 2.46. Whew, that's one of our answers. We're good. Always great when you got a multiple choice question and one of your answers, or one of the answers, is your answer. Makes you feel much better, doesn't it? All right, so that is our pH 2.46. So it's still very, very low, right? We've actually added quite a lot of sodium hydroxide. And in fact, more volume of sodium hydroxide than we did acid. But remember, it's not the volume that matters, it's the moles that matter, right? What do we have left in there? Things react on a mole basis, not a molarity or volume basis. All right. So that was the end of that one. I didn't pay attention to my own notes. That was the end of that one. Titration, strong acid, strong base. Calculate the millimoles of each of them. Figure out which one you have excess of. That's your concentration. Find your pH or your pOH. Then find your pH. Thanks so much and have a wonderful day.